Let us continue with the 2D array address calculation. Let us see one more example. Given a two-dimensional array which is ranging from 1 to 8, column ranging from 7 to 14, stored in row major order with base address 100 and size of each element is 4 bytes, then find address of the element which is stored at index 4 and 12. First of all, we have to find values for m and n, okay, and the other values given as these. So first of all, the value m, which can be calculated as upper bound of row minus lower bound of row plus 1. So upper bound of row is what? 8. Lower bound of row is 1. Upper bound of column is 14 and lower bound of column is 7. So upper bound of row, which is 8, minus lower bound of row is 1 plus 1 is 8, and the value of n can be calculated as upper bound of column minus lower bound of column plus 1, which is given as 14 minus 7 plus 1, which is 8. So now we have values of m and n. Now we can proceed with address calculation and we can find the address using this equation. So we have base address which is given as 100 plus size of element is 4 bytes multiplied by total number of rows m, which is 8, and total number of columns n, which is 8. So 8 into the given value of I is 4 and j is 12. So I would be 4 minus lower bound in row is 1, so 4 minus 1 plus given value of j, column index is 12, minus lower bound of column is given as 7. Okay, so let's write 7 here and let's reduce this. So 100 plus 4 times 8 into 3 is 24 plus 12 minus 7 is 5. So 24 plus 5 is 29. Okay, and 29 multiplied by 4 is 116. So it is 216. So here 216 is the address of element which is stored at 4th row and 12th column. Let us see one more example. Derive the formula to calculate address A of ij of 2D array for a row major order storage representation. A 2D array defined as RC. R stands for row and C is for column. So here lower bound and upper bound are given in terms of range. Okay, so here lower bound of row is 1, upper bound of row is 4, lower bound of column is 5, and upper bound of column is 8. It requires 2 bytes of memory, so W is 2, and if array is stored in row major order, then calculate the address of A37. Means here I is 3 and J is 7 and the base address is 2000. So here are the values which we are given and we need to find m and n. Okay, so value of m would be upper bound, which is 4, minus lower bound plus 1, so that would be 4, and value of n will be upper bound of column minus lower bound of column plus 1, so that will also be 4. So let us put all these values in row major equation, that is base address which is given as 2000 plus W is given as 2 bytes of memory, N is given as 4 into I we have 3 minus lower bound of row is given as 1 plus J is 7 minus lower bound of column is 5. Okay, so it would be 2000 plus 2 into 4 times 2 is 8 plus 7 minus 5 is 2. So 10 into 2 is 20 and final answer is 2020. So the element at index 37 is stored at 2020 address. The next topic is matrix representation of polynomial equation. So if we are given polynomial equation like this and it is having one variable, okay, so in this case we can represent this polynomial in terms of one-dimensional array. So in this equation we have highest power, which is 6. So we will create an array with the indexes which ranges from 0 to 6. Okay, whatever values we have written in this array represents the coefficient values, and these indexes represents power of the variable x. So this represent x raised to 1, x raised to 2, x raised to 3, and so on. Okay, so with x raised to 6 we have coefficient 4. So in this cell we would put 4. Okay, here x raised to 1 has coefficient -2. So at x to the power 1, at first index we will put -2 as coefficient, and here we have constant 5, but this x term is absent. So we will put x raised to 0. So at x raised to 0 we will put coefficient 5, and rest of the values will be 0 as we don't have any coefficient for these terms of x. Let us now see the representation of polynomial 2x square plus 5xy plus y square. So in this example we have two variables, x and y. Okay, and this represent x to the power 0, x to the power 1, x to power 2. This represent y raised to 0, y raised to 1, y raised to 2. Okay, so now in this equation we have x term but y term is absent, so we will put it as 0. Then we have 5x raised to 1, y raised to 1, and we don't have any x term, so constant will be 1. Then it will be multiplied with x raised to 0 and y square. So the indexes which we get is 2 0, index 1 1, and index 0 2. So at 2 0 index, x raised to 2 and y raised to 0, we will put coefficient of this particular term. So x square, y raised to 0, we have coefficient as 2, right? At index 1 1 we have coefficient 5, so we will put 5 here. We have 0 2 index, and at 0 2 index we have coefficient 1. Okay, so this is the final matrix representation of the polynomial equation having two variables. So this matrix have less number of non-zero values and more number of zero values. Such a matrix is called as sparse matrix, which we will see in detail. So let us see multidimensional arrays first. Multidimensional arrays is nothing but array of arrays. So it has multiple dimensions. In one-dimensional array we have one dimension. In two-dimensional array we have two dimensions. So in multidimensional arrays we have n dimensions. Okay, so in real life example, if we say that a page is a 2D array which has a width and height, okay, so that is a 2D array, and if we add depth, means third dimension, to the pages, then it will create a book. Okay, so let us see how multidimensional array is stored in memory. So let's take example of three-dimensional arrays. So in case of three-dimensional array, we have three dimensions. So suppose this is a book having multiple pages. So as we have described, it is array of arrays, means this will create a 3D array of multiple 2D arrays. And if we assume that this is the first page of book, this is the second page of book, and this is third, and up to n pages of book, okay, then these first Then all these pages creates a depth, means third dimension, and then we can have a book. Fine. So how do we represent this array of arrays in memory? So let us see indexes first. This is 0th row, 0th column and 0 depth. 0th row, first column, 0 depth. 0th row, second column and 0th depth. Here indexes represent row, column and depth. Okay, so in first page we have depth 0 at all the places. In second page, third index represents depth, that is 1. In third page also depth 2 and so on. Okay, so this represent page 1, page 2 and page 3, that is array of arrays. Okay, so we can store these values in memory like 000, 001, 002 and so on. Okay, then we will have 010, 011, 012 and so on. Okay, so this is how we can represent this 3D matrix in memory. Let us now see the applications of arrays, where arrays are used. So arrays are widely used to implement mathematical vectors, matrices as we have already seen, and other kinds of rectangular tables. Many database records are stored using one-dimensional arrays. So for example, if we want to store marks of different subjects in one-dimensional array, then that is possible using arrays. Arrays are also used to implement other data structures such as string, stack, queue, heaps and hash tables. Okay, so we will see how do we implement stack and queues using arrays. Then arrays can be used for storing elements in ascending or descending order. So in case of sorting and searching, we can use arrays. Let us now see what is sparse matrix and how do we represent sparse matrix. So we had already seen what do we mean by sparse matrix. So let us see the definition. Sparse matrix is a matrix that has a large number of elements with a zero value. Means a matrix which have more zero values than non-zero values. Such type of matrix is known as sparse matrix. Sparse data can be easily compressed, which in turn can significantly reduce memory usage. Okay, so the matrix which is having more number of zero values can be easily compressed so that we can have only significant information with us. So we can have only necessary information which is non-zero values with us. Let us now see the array representation of sparse matrix. Suppose we are given this sparse matrix. Then in order to store or compress this sparse matrix, we would have to maintain some information, that is row number, column number and non-zero value of this sparse matrix. So we need these three information in order to compress this sparse matrix. So let us see how we can represent the sparse matrix in terms of array. So we will record first non-zero element, which is 4, and that value 4 is stored at 0th row and second column. So it is stored at 0th row and second column. The next non-zero value is 5, which is at 0th row, 4th column. So this 5 value is at 0th row and 4th column. Then next non-zero value is 6, which is stored at first row and second column. So first row and second column and so on. So this is how we can represent sparse matrix in terms of array. Let us now see the linked list representation of a sparse matrix. So we can also compress sparse matrix using linked list. We can represent sparse matrix using linked list also. So here we need to keep track of 4 values, that is a non-zero value, row number, column number and address to the next node. As in linked list, elements are stored sequentially but by means of links. So these nodes are stored randomly. So in order to link all these nodes, we have to provide address to the next or upcoming node. Okay, so here one extra information we have to keep is address information. Okay, so we can represent sparse matrix as compressed form of linked list like this, in which first we will store row index, column index and the non-zero value, which is 4. Then we will at last store the address to the next node. So this last value is address to the next node. Okay, in next node we will store next non-zero value, which is 5, and 5 is stored at row 0 and column 4. So at 0th row and 4th column we have a non-zero value, which is 5. Okay, so suppose this element is at address 1000, so this address will be the address of next node, and suppose this is at 2002, then here this will be having value 2002 that represent the address of the next node in memory. Okay, so this is how we can represent or compress our sparse matrix using linked list.